Okay, so this lecture is about transformer equivalent circuits in simplified form for full load condition. Now for full load condition, so here is the load side, I2, which is the current flowing in this branch in here. So I2, which is the load current, is very large. If I2 is very large, then this I2 prime in here is going to be very large as well, and you know that your I1 is made up from I2 prime and IE1 when we are assuming the full load or condition. So that means we're assuming I2 prime is very large. In that case, we can say that your excitation branch current I1 can be ignored in comparison to the other currents in here. So if we can ignore this current, that means under full load conditions we can ignore this whole branch. So what we will be left with is only this branch in here and this branch in here with the transformer. So this is how your simplified equivalent circuit for full load conditions is going to be looking like. So from here we have removed that branch which represents the impact of the core loss and the magnetizing current. Now this circuit still has this transformer, the ideal transformer in here. So if we refer these values to primary side, we can get rid of that part. So here we are referring the whole circuit to primary side. So your R2 is converted to R2 prime, A square times R2, and LL2 prime is also converted to A square LL2, which is your LL2 prime, and it's the referred value of the inductance to the primary side. Now, and the secondary current and the secondary voltages are also so. So this is a simplified model for full load conditions, and it's referred to primary side. And now you can see all these four components are in series, so you can combine them. So you can sum them up. So you can do R1 plus A square R2 to make one resistance, and you combine these two as well to make one inductance. So in this case, we have combined both resistances into these into RE1 and both inductances in here. So your RE1 basically equals to R1 plus A square R2, and at the same time your LE1 equals to your LL1 plus A square LL2. So RE1 is the total resistance for primary side and the referred secondary side resistance, and the equivalent inductance is again the primary side inductance plus the referred inductance from your secondary side. And you can convert this inductance, of course, to the reactance, because that's going to be playing its role for impedance. So your X equals to omega times L, or 2 pi FL. That still applies to this one. So in phasor form, you have to have an X in here, and X is, of course, with a J angle 90 degrees. So it's a reactance, as I explained earlier in this class. So your this is your R and your X at an angle of 90 degrees. So X in here, R in here. So this is going to be where your Z is going to be. So your Z is basically R square plus X square square root. So that's going to give you an amplitude, and its phase angle, let's say phi, is going to be this one in here, which you can find with many different ways, and one of them is tangent inverse of X over R. Okay, so this is your equivalent circuit simplified for the condition of full load. Here is again we're having the complete equivalent circuit, because we need a complete equivalent circuit for many conditions anyways. So this is your complete equivalent circuit back, but you can see there, here you don't see any transformer. So this is the complete, not under full load or no load conditions. This is the complete equivalent circuit, which has the impact of the winding resistance and the leakage inductance, which also has the impact of the core losses and the magnetizing current. But this circuit is referred to primary side. So you have the primary side values as it is, and you have the secondary side values referred to primary side. So even under this condition, you can see that your load is the ZL prime, which is A squared times the ZL. So your RE1 is going to be R1 plus A square R2. Similarly for your inductance, it's going to be your primary side inductance plus A square times your secondary side inductance, because you need this complete circuit for efficiency calculations, where you need to know both core losses represented by this RC and the copper losses, which is represented by this RE1 in here, RE1 and RE2. So you need the equivalent circuit, but with that transformer up in here and the primary side values to primary side and secondary side values to secondary side, it's very difficult to solve that circuit. So that's why we have simplified it to bring this branch to one side and the resistors and the inductors to the other side. Now in phasor form again, so you instead of inductance you have X in here, and all the values are in their phasor forms. This one is a circuit although referred to secondary side. So you can see that your I1 is I1 prime, your V1 is V1 prime, and these values are also to the secondary side, and your source is referred. And you can see that your secondary side values are now just direct by themselves. So this is again the complete equivalent circuit, but this is referred to secondary side. So you need the complete circuit represented in this slide and in this slide for efficiency calculations. Thank you.